Now we're going to learn how to write Lewis structures for covalent compounds. So we're going to go through the steps. These are kind of a guideline, and then we'll do some examples, and then we're going to play with the model kits and do some of this in lab today, and I think it'll be really helpful. So the first step is to write the correct skeletal structure for the molecule. So we're going to deal with molecules. They've got more than one atom, and so we have to figure, well, how are those atoms connected to each other? That's the skeletal structure. Sometimes you have choices. There's more than one way you could arrange the atoms. Hydrogens always have to be on the outside. We say they're terminal atoms because they can only make one bond. Hydrogens only make one bond, so they can't be in the middle and have two different atoms bonded to them. Another guiding idea is that many molecules tend to be symmetrical. So if you have NO3 or SO4, the odd one is going to be in the middle and the multiples are going to be around it. So SO4, the sulfur would be in the middle and the oxygens will be around it. There are many exceptions to that rule, unfortunately. I know students do not like exceptions. Sorry. Step 2 is to figure out how many valence electrons do you have to mess around with here. We're going to be drawing the dots and the lines, and we can only use as many valence electrons as those atoms actually have. So, if you've got CO2, you've got carbon, you figure out, well, how many valence electrons does a carbon atom have? And if you've got 2 oxygens, how many valence electrons does each carbon atom have? Multiply by 2, add them all up, and that's the number of valence electrons. And that tells you how many dots you can put into your structure. If you have an ion, if you have a negative ion, every negative charge means you've got an extra electron, so you have to add 1 to your total. If you have a -3 ion, you have to add 3 to the total of electrons. If you had a positive ion, you would have to subtract for each positive charge. Then you take those electrons and you divvy them up. And don't get hung up on who brought which electrons. In Chem 3A, we don't care about that. So imagine these atoms coming in and they're putting all their valence electrons in a big bowl in the middle of the table, and then they're going to share them so that everybody can be happy. So don't worry that, but this one has to be over here, or where does the extra electron go? Don't worry about that. So you start out by putting 2 electrons between each pair of atoms because there has to be a bond. Otherwise it wouldn't be a molecule. There has to be something holding them together. So put single bonds between all the atoms, and then take the rest of them and distribute them as dots, and try to get everybody to have an octet of electrons. And sometimes you can just spread them around and everything's good. Of course, remember that hydrogen only needs 2 electrons. So hydrogen never has a lone pair because hydrogen is got the one bond, and the one bond makes hydrogen happy. Sometimes, though, you start spreading those electrons around and you realize you don't have enough to make everybody happy. When that happens, you need to make multiple bonds, either double or triple bonds. And so you move some of those lone pairs that you put, and you move them into bonds. And we'll do some examples. It's like reading the rules of a board game doesn't make a lot of sense until you start doing it. So let's do carbon monoxide. So the first thing we need to do is to make a skeletal structure and figure out how are those 2 going to be connected. Well, for a diatomic molecule, only 2 atoms is pretty simple. They're going to be next to each other, right? So the carbon's going to be bonded to the oxygen. And then we have to figure out, well, how many valence electrons do we have to deal with? So we look at carbon in the periodic table. It's in group 4. We have 1 carbon, so there's 4 valence electrons. We find oxygen. It's in group 6. And so we add those together, and we have 10 valence electrons. So we have 10 dots that we can use in our Lewis structure. We have to start by putting 2 between the carbon and the oxygen. There has to be a shared pair there, a bond. Then we're going to distribute the rest of them. We've got 8 left. So I tend to count by twos as I do this. They're always going to end up in pairs. So I've got 2, 4, 6, 8, 10. I ran out of dots. I ran out of electrons. Do both of these have an octet? No, neither of them has an octet. What can we do about that? Well, I could take this pair off of the oxygen and put them over there so carbon has an octet, but now oxygen isn't happy, so that's not going to work. We don't have enough electrons, so we need to share more. So we take one of these lone pairs and we make it into a bonding pair. I didn't leave much space here. I'm going to fix that just because I can. I'm going to move this guy over just a smidge. So we move that pair in there. We still have 2, 4, 6, 8, 10 electrons. But now we're getting closer, aren't we? Each of those has 6 electrons now. Wait a minute. 2, 4, 6, 8. 2, 4, 6, 8, 10. Yeah. The carbon has 8. The oxygen has 6. Forgetting how to count. Are we good? Is everybody happy? No. We can't stop until everybody's happy. Okay? It's not the real world, obviously. So we need to share some more. So we're going to take one of carbon's lone pairs and we're going to share it between. Now let's look with the orange circles at what we've got. So carbon is counting all of the shared and its lone pairs. 2, 4, 6, 8. Oxygen is counting all of those shared electrons and that lone pair. 2, 4, 6, 8. 8 valence electrons. So the orange circles are not part of your Lewis structure. You might want to copy that, recopy that, make it look a little nicer. If you do it with the lines instead of the dots for the bonds, then you'd have 3 lines for a triple bond. And maybe you would want to put these over there just because it looks nicer. I don't know. But if you put them on the top or the bottom or the side, it doesn't matter. That's the Lewis structure for carbon monoxide. Any questions? So carbon monoxide has a triple bond. Let's do H2CO. Well, the first thing we have to do is figure out the skeletal structure. So there's many different ways that we could put these together. What if we did this? Would this work? Wait, I don't want to put a line. HHCO. Could that work? No. Because hydrogen cannot be between 2 other atoms. It has to be on the end. Well, so that means that the hydrogen must be next to the carbon. A lot of times the way they write the formula is going to give you a hint. This is not the best example. And then where are we going to put the other hydrogen? We could put it over here. In fact, let's just do that, even though it's not right. But you have no way of knowing that that would be not right. So let's just go with it. How many valence electrons do we have to deal with? Well, we have 2 hydrogens. They each have 1 electron. We have a carbon with 4 and an oxygen with 6. And so that gives us 12, right? So then we start putting electrons in between because you have to have a bond. So there we've got 2, 4, 6. We've got 6 more that we can put out. Hydrogens don't need any more. So there's 6, 8, 10, 12. Are we happy? No, we're not happy. What can we do about this? Well, we're going to have to move some electrons. So let's take these electrons and share them between the carbon and the oxygen. We can't do any extra sharing between hydrogen and anything else. Hydrogen forms one single bond. That's all he's capable of. Is this good? No. Carbon only has 6 electrons now, and oxygen has too many. It has 10. So oxygen's got too many, so let's take away from the one with too many and give to the one that doesn't have enough. That sounds like Robin Hood, doesn't it? Now does everybody have 8 except hydrogen with 2? Yeah, so we could rewrite this H, C, double bond, O, H, and put in lone pairs. That's actually not what this molecule looks like. So is it possible to draw acceptable Lewis structures for molecules that don't exist? Well, kind of. There's some little rules that the book hasn't told you about. So I'm going to, try to show you what those are. Okay, so let's look at carbon and oxygen. Carbon has 4 valence electrons, and we learned that we should put those around by themselves before we pair them up. And oxygen has 6, so it's going to end up with 2 that are paired and 2 that are unpaired. If we look at those Lewis structures of the atoms, the number of unpaired electrons in their Lewis structure is the number of bonds that they tend to form. Oxygen usually forms 2 bonds, and carbon usually forms 4 bonds. In our structure, is that the case? Oops. wrong part here. Here we've got carbon with 3 bonds, a double, which is 2, and this one. And here we've got oxygen with 3. So that's not the ideal structure. I would not expect you to be able to predict that, at least not yet. So this is the actual structure. It's going to be the carbon and the oxygen and the hydrogens off of the carbon. So 2, 4, 6, 8, 10, 12. So if we do it that way, we can still have octets for the carbons and the carbon and oxygen. And now how many bonds does carbon have? It's got 4. And oxygen has that one double bond, which is 2 bonds. And so this is the correct Lewis structure. What's cool about the lab we're going to do and playing with the model kits is that the balls have certain numbers of holes in them, and you wouldn't be able to make a model of that first molecule. Any questions? What about ions? Well, writing a structure for a polyatomic ion is essentially the same, except that we have to adjust the number of electrons. So if you have a negative ion, you add 1 for each negative charge. If you have a positive, you subtract 1. So when you have a polyatomic ion, ions are where you have the brackets, and so you put a bracket around the whole thing and put the charge on the outside. So let's do an example of that. Here's the cyanide ion. First step is the skeletal structure. And then, so 2 atoms, they've got to be connected to each other. That one's easy. Then number of electrons. So carbon has 4 valence electrons. Nitrogen has 5. There's a charge on this. It's an ion. A -1 charge means we have an extra electron. A lot of times students see that minus and they want to subtract 1. It's very understandable, but You have to add one. So we get a total of 10 valence electrons in this ion. So we have to put 2 in between. So there's 2, 4, 6, 8, 10. We don't have enough. Always start with single bonds and put the electrons around. If you run out of electrons, then make double bonds. So I'm going to take this one and put it in here. Or better, do we have 8 for everybody? No, the carbon has 8, but the nitrogen only has 6. So we have to do this again and form a triple bond. So on the worksheet today, use pencil. There will be a lot of erasing. Use a pencil. And then we put brackets around it and a negative because it has a -1 charge. The other way to write this one is using the lines for the bonds. That's a triple bond. And then putting the dots in, the lone pairs. But again, put brackets around it and the negative on the outside, the charge. So that's the Lewis structure for cyanide ion. Let's do one more. What's the name of this ion? Do you remember? It's related to chlorate. Chlorate was ClO3 minus. Chlorite was O2. This is hypochlorite. A little review from chapter 5. So chlorine and oxygen. And chlorine has 7 valence electrons. Oxygen has 6. The -1 charge means we add 1. So we're going to get 14 valence electrons to distribute. So we have to put 2. There has to be at least 1 bond between the 2 atoms. So there's 2, 4, 6, 8, 10, 12, 14. Oh, look, we had enough. Great. We don't have to make a multiple bond. Then we put the brackets around it and put a charge on it because it's an ion.